You're probably familiar with how diffusion is used to generate images. Start with noise, then denoise it over steps. At each step, the picture gets clearer. Each pixel turned from noise into signal. And crucially, every pixel is looked at simultaneously, at each step, the entire image considered in full context. Go over enough steps and the noise becomes a crisp image, exactly as the prompt described. Here's a question. Could the same approach work for text generation? What if you could give a model a prompt and have it denoise a sentence into existence? How would that work? And more importantly, what would it get us? To see why that would be different, start with the way text generation works today. Every large language model you've used generates text like this, one token at a time, left to right. Token 3 can't be chosen until token 2 exists. Token 2 waits for token 1. Each word is conditioned only on what came before it, never on what comes after. No revision, no backtracking. Once a word is committed, it's committed, and every decision is made with only half the context, the left half. But borrowing diffusion from images creates one immediate problem. An image can be 10% noisy, 50% noisy, 90% noisy. It's a continuous value, corrupt it by any amount you want. But how would we translate this to text? What's the equivalent of 10% noise, or 50% for a sentence? A word is discrete. River is either there or it isn't. There's no 30% river. So instead, we mask the tokens, mask 1 of 9, that's 11% corrupted. Mask 5 of 9, 55%. Mask all 9, and the sentence is fully corrupted. Noise in pixels equals masking in tokens. Once masking gives us a version of noise for text, the rest starts to look more like diffusion again. Step 1. The model scans all 9 positions in a single forward pass. Every masked position gets a prediction, in parallel. 2 come back with high confidence, river and stone. Those get filled, 2 done, 7 to go. Step 2. The model again scans all 9 positions. It makes predictions for all 7 remaining, picks the highest confidence ones. 3 more tokens get filled. Step 3. Finally, the model makes predictions for the remaining 4 positions. The sentence is complete. And something interesting starts to happen. The content words, the ones carrying the most meaning, emerged first. Then more tokens filled in around them. The function words filled in last. This is something an autoregressive model doesn't do. It fills in the next token no matter how unsure it was about what comes next. That's the important shift. The diffusion model isn't racing from left to right. It's letting the sentence come into focus, one confident iteration at a time. And this isn't just a different way to generate text, it's a completely different workload for the hardware. Here's what autoregressive generation looks like to the hardware. 9 tokens, 9 sequential forward passes. The GPU does a burst of work, then waits, then another burst, then waits. Most of the silicon sits idle. Diffusion. 3 steps, but each step processes all 9 positions in parallel. 1 forward pass covers every token at once. The GPU stays saturated. The hardware was designed for exactly this kind of parallel work. For a short sentence, the difference is modest, but as sequences get longer, hundreds of tokens, thousands, watch the gap. The sequential approach grows with every token. The parallel approach barely changes. Make it concrete. A 512 token response, autoregressive, 512 sequential forward passes. Diffusion with 64 denoising steps, 64 forward passes, regardless of how long the output is. The sequence length drops out of the equation. So, when more of the work can happen in parallel, what does that actually translate to? Same prompt, same model size. One generates left to right, one generates everything at once. Autoregressive. 1 token, then the next, then the next. Diffusion, the whole response crystallizes in a few passes. Look at the tokens per second. Autoregressive around 50 tokens per second. Diffusion over 1,000. Same answer, same model size, the sequential bottleneck removed. That's the difference. The hardware was always capable of this speed. Autoregression was the thing slowing it down. But speed alone doesn't decide the whole story. Diffusion language models haven't replaced autoregressive ones across the board. There are honest gaps, open-ended reasoning, long-form coherence, creative writing. Autoregressive models still lead on tasks like these. The gap is narrowing with each new paper, but it's real. This architecture is promising, not dominant, not yet. So the point isn't that diffusion replaces autoregressive models overnight. It doesn't. It's that it changes the framing entirely. Modern language models taught us to think of generation as next token prediction. Given everything so far, what comes next? Diffusion changes the question. Given the whole shape of the answer, what's still missing? From writing one token at a time to shaping the whole answer into place, that is a real paradigm shift.